All right, everybody, let's throw this in the better late than never category. So let me go through these slides, and I'll talk about some extra stuff from rate as well from when I was gone. So when we're looking at these two graphs, we're really looking at equilibrium here, right? We see the reaction above, and equilibrium is where in these circled areas, right, where we see that the concentrations appear constant, right? Looking at all of these circled areas. The concentration is no longer moving. As time goes by, the concentration stays constant. But remember, we learned that this is a form of actual dynamic equilibrium that's going on. And so what's actually happening is the forward reaction and the reverse reaction are both still happening, right? A is getting used, C is getting produced, C is getting used, A and B are getting produced. All of that is all still happening, but it's happening, the forward and reverse reactions are happening in the exact same rate, at the exact same speed. So every time you make a product, you also are making a reactant with one of the other reactions going on in the beaker or whatever. So we see that, that there's that flat line, right? But don't be confused. The reaction does not stop. The other thing we notice with these graphs is the ratio of C to A and B remains constant, right? So we see two things here. With the first two graphs as compared to the last, we see the last one has less stuff. It has less total amount of reactants, or of whichever is being measured here. But the ratio of the red, of the, the green line to the red and blue lines is intended to be the exact same ratio, even though the actual values are a little different. And when we look at the first two graphs, we see that whether we start with reactants and not products, or we start with products and no reactants, we get to the same place in the end no matter what. That's equilibrium, right? It's like, it's an inner defining feature of this reaction. Any given reaction will find its equilibrium position. And that took us on to looking at our Kc value, our Keq value, and that's that ratio of product Keeneland. But right, the rate of the K value for any given reaction is going to equal the concentration of the products over the concentration of reactants. But more specifically, let's take the reaction above here. It would be concentration of C divided by concentration of A squared, right? We take the coefficient from the balanced equation in front of each thing, and that becomes the power that concentration is raised to in this equation. And then we would multiply by B. There was some confusion in class. Those factors, those concentration factors in this equation, it's multiplication. There's no addition or subtraction here. It's all multiplication. So this is for your K values, right? Concentration of any of the products times each other, all raised to their own powers from their coefficients over the reactants. So always products over reactants. So then we took that and looked at scale, at the size of K values, right? So if we have a K value that is greater than 1, looking at this equation, we see that the reaction must favor the products, right? If we have a K value less than 1, right, that means the bottom number is bigger, meaning there's more reactants, meaning the reaction favors the reactants. Right, so that's that little blip from looking at those equilibrium constant values. Now, remember, with the math here, it's all algebra. You'll be missing one variable, and that's it. The most confusing, trickiest stuff you'll get is maybe you'll be thrown a cube or a to the fourth that you have to then root out to get to a known concentration value or something like that. But that's it. It's just algebra, okay? So rearrange your equation, solve for the thing you're missing, and then you're good to go. Okay, for reactants, when you did with about a little rate at the very end. All right, here we go. So then we talked about Le Chatelier's principle, and that's the idea that if we disturb a reaction and make it off from its equilibrium, the reaction will shift to fix it, either towards the reactants or towards the products. So we saw that it was pretty easy to think about with concentration, right? Which side of that teeter-totter gets heavy? That's how I like to think about it, or light, whatever, and then trying to get it back to balance. So if we add some reactant, the reaction will shift to the products to use them up. If we take away some products, or no, that's a reactant. If we take away some reactants in the blue one here, now that makes the reactant side not have enough stuff. The reaction will shift back towards the reactant side to fill that back up, to fix it. The tricky one we saw, well, not even tricky, but thing to remember is that temperature, right? Remember, temperature changes that permanently. Temperature will change your equilibrium value, but nothing else will. And that's why a lot of those problems had a temperature component. on them. It just told you the temperature. You don't need to do anything with that necessarily. It's just, it matters because at a different temperature, there would be different values. So here we see heat is like a product, so this much must be exothermic. So we can think of it really simply just like concentration if we want to, and then remember that it's permanent. So if we add some heat by adding the temperature or increasing the temperature, product side becomes heavier, shifts towards the reactants, and then we have to remember that's a permanent shift towards the reactants. So now we have more reactants, K is products over reactants, therefore the K value would decrease. Okay, so kind of remembering, be really systematic when you work through those. With pressure or volume, again, I always really like to think about it as volume. When we're looking at these, now, the shifts that result affect the entire reaction, of course, but when considering whether there's a disturbance or not, we need to only look at the gases, okay? So, because if we squeeze the solids or the liquids, it doesn't matter. We're not going to compress liquids and gases in the scales that we're talking about here. So, you want to just look at the number of moles of gas and imagine that the reaction wants to stay as spaced out as it currently is. So if you increase the pressure, like the example here, which is decreasing the volume, you're making there be less space. If there's less space, the reaction will shift to make less moles of gas. So 3 moles on the right, 2 moles on the left, the reaction will shift left. Okay? If we were to increase the volume or decrease the pressure, we'd be creating more space, so the reaction would shift to the side that would make more moles of gas. Less with less, more with more, if you're thinking about volume, which is the way I do it. And then we, of course, talked about how solids don't play a part in this. Obviously, the amount of solids or liquids would change as the reaction shifts, but they have no concentration, and they don't play any role in determining equilibrium shifts or in any of our equilibrium calculations. Right here? Oh, I don't have it here because that was in your other notes. So here we looked at some of these problems. We can fill in a few more answers here if you want. Well, let's skip over here. Those ones were pretty straightforward. Let's come down to the one that's not an all gas equation. So here we have sodium hydroxide. It's a solid. If we add some, that's not going to change anything. If we already have some, we already have some. So there will be no change to any of these things. Okay. If we add some sodium chloride, that adds sodium ions. That makes our product side heavy. So that's going to shift us towards the reactants. Amount of NaOH. So here we see that it says amount instead of concentration. So I'm going to say, yeah, sure, we'll make more. It's going to the left. Again, we can't talk about the thing we changed, and adding NaCl changed Na. We would, however, decrease in our amount of hydroxide ion, and still, though, the K value would not change. Adding KOH would have the exact same effect because we're adding a different product. So I'll keep all my arrows the same, and again, that doesn't change. Adding H+, so this was like one of the, we did an example like this, I forget when, where the thing we're adding isn't directly involved in the equation, but it interacts with something that is. So here, if we add hydrogen ion, it's going to react with that OH. H and OH will always make water together. So really what that's doing is removing hydroxide ion. So we're removing a product, so the reaction will shift to the right to fill it back in. Therefore, we're going to get a decrease in the amount of sodium hydroxide, right? More will get taken. And we'll get an increase in our sodium, and we will get a, what happens to K? Nothing, right? It's not temperature. Here we go, temperature. It's exothermic, right? We see that heat is on the product side. Therefore, if we increase temperature, we add heat to the products, we add products, think of it that way. That side gets too heavy, shifts to the left to use it up, right? So we're going to shift to the reactants. So our arrows will follow all of those shift to the reactant arrows, but this time it's permanent. So we made more reactants. It's always K equals products over reactants. So if we have, see there's an E in there. If we have more reactants, we have a smaller K value. Okay. Decreasing Decreasing temperature removes some temperature, some heat from that product side. So kind of like removing products, shifting the reaction to the right to make up for it. So we would get everything opposite to what we did prior. And including an increase in the K value, right? To shift to the right makes more products, a higher K value. Let's look at pressure. Yeah, nothing happens, right? Why does nothing happen? Because there are no gases in this equation. There's no gases, we don't, a change in pressure or volume will not change anything. All right, let's look at a couple of these I think the first page was pretty straightforward. Let's look at some of these bottom ones. I'll go through a few on the bottom. I don't think we'll do all of these. I know there were some people that had a hard time with this bottom one here, right? So if it during in moist air or dry air. So think of moist air as being full of water and dry air as not. So if you have air full of water, that water is probably going to be added to the reaction. Therefore, we are adding some product. The reaction would shift to the left to use that up. So it's going to incorporate the water. This equation does not look balanced to me, so hopefully you didn't look too closely. But I do believe that moist air would be pink, and that's our moist air, okay? And I don't know, I don't think we're supposed to put anything on that line. Whatever, it doesn't matter, right? Pink would be moist air. There's water in the air. That adds to the product side, shifting the reaction to the left, okay? It's just like when we did our formula, the hydrate lab, right? We were able to add heat and that drove off the water, right? Remember, and then it changed color. It got a little light blue. And then if we added a little bit more water back to it, we did a couple drops and we saw it turn really, really, really dark blue because that compound, even though it was still dry, it had absorbed the water into the compound. All right. So let's look at number 9. What would be the effect on equilibrium position? Carbon, oxygen, carbon monoxide, if the total pressure were decreased, right? So we're looking at a pressure and a decrease. So total moles of gas. Let's see here. Are we balanced? We are. So I have 1 mole of gas over here and I have 2 moles of gas over here. So if I am decreasing the pressure, I am taking away some pressure, which means I'm giving it a little more volume. If I'm giving it more volume, they're going to want to make more gas. So it's going to shift to the right. Okay. Blah, blah, blah. Here we go. Pressure decreased. They like pressure decreased, don't they? Wow. You'd think they could ask the opposite question on this one. Sorry, guys. Let's change this one and call this one increased just for kicks. Okay, so if we increase the pressure here, just to make it a little different, increasing the pressure is like decreasing the volume. So again, we have 2 moles of gas on the left, and now it looks like we have 6 moles of gas on the right. So if we are going to increase the pressure, right, I'm changing the problem just to play with an increase. Increasing the pressure means I'm smushing it all down, I'm making there be less space, so this reaction can go from having 6 moles from the reactants and combine those and make them only 2 moles of the reactants, from the products to the reactants, sorry. So it's going to do that. It's going to take up less space. So increase the pressure, meaning you decrease the volume. Less volume, you make less molecules. So this one's going to shift to the left. So again, I think that should get you through those. Excuse me. So again, here is the key to the quiz. Again, we talked about, size of our K values. Our equilibrium constant expression, and then using it in a variety of ways, right? Again, number 4 here is probably the most complex you'll have to do, dealing with roots and stuff like that to get that unknown concentration. And then up here, let's remember for our explanation for B, right? I've talked about it a little earlier on, but if we increase the temperature, right, we have a reaction here that is endothermic. So by increasing the temperature, we are adding heat kind of continuously to keep that temperature up. So temperature produces a permanent change in the K value, the permanent shift. So whatever direction it shifts, it doesn't ever go back. It doesn't ever, and that there's none of the concentrations in the equation to make up for that mathematically, right? Because it's the heat that's moving it. It's not a change in any of those concentrations. So you end up with a different ratio. So that K value does change. If it shifts to the right, we get more products. More products is a larger K value, and that's why. And then again, formatting on these, absolutely use arrows. Arrows and equal signs are just fine. And then number 7, right? How can we think about how we could manipulate an equation? Make sure you can do that. I wanted to just really quickly talk with you about rate. So again, when we're looking at a rate of reaction curve, it can be, an increasing amount of products, and it could also just as easily be a decreasing amount of reactants. Doesn't matter, right? You're just measuring some value that represents the amount of products or reactants. It could be volume of a gas, it could be concentration of a product, it could be change in mass, it could be whatever. And then it's time along the x-axis. So remembering, there are 3 different ways that we measure rate, right? We'll measure our initial rate, It's going to be like the first 10 seconds, the first 5 seconds, whatever. It's that very initial slope. You find that the most of that straight line that you can get, and then get the slope rise over run. We could do the rate at a point, at any point, right? So here, we would have our scale on the bottom and on the top, and we would take, and this would be what the black one would be 2/1. So the initial rate would be 2. Right? We could take the rate at a tangent at any point along the way. So I could say, okay, I want to know what the rate is right there. And then I'm just going to try my best to make a little tangent line. Is it basically impossible for you to do that by hand? Yeah, absolutely. So, be careful with it and do your best and you'll be fine. Right? So there we go. So I could drop down and imagine maybe that's a 1/2. Give or take, maybe it's a 1. Yeah, there's 2 under there, right? A 1/2. So clearly different. Now I have a half. I went from a rate of 2 whatevers per time to a half over per time. So then we can take the average. And for the average, again, you just, once the reaction really flattens out, it's done. It's not going to be changing. There's nothing else going on. So then again, you get your straight line and you just take your average, whatever that may be. And I don't know what that would be. Or here, 1, 2, 3, 4. I mean, maybe this is going to be 6/15 or something like. I mean, it's going to be smaller, right? So notice the rate of the reaction is slowing down as it goes. This should make sense if we think about collision theory. The reason a reaction happens is that particles collide, and they do it with enough energy and the proper orientation. They have a successful collision, and so the things that affect that, right? We talked about this. You talked about this. Particle size, right? Surface area, that kind of idea of if there's more exposed molecules or atoms, you'll get more reactions. We talked about concentration, right? If there's more stuff around, the likelihood of them smashing into each other, the more likelihood of them smashing into each other is higher. We talked about temperature, right? If we increase the temperature, they're moving around more, they're smashing into each other more, and when they do, they have more energy, so they're likely to go faster. What else? We talked about adding a catalyst, right? That's just going to make it go faster in general. It's going to give it a different pathway that's just easier to do. Therefore, needs less energy. Therefore, at the same energy, you have more successful collisions. So being able to talk about that, being able to talk about those factors that will affect the rate, just like from our lab, and being able to determine the rate in this graphical approach, in any of these three methods. Okay, I will see you Monday again. Sorry it's a little late, but enjoy the rest of your weekend.